Drugs, yeah, that's the answer. Drugs is the answer.
No, I'm gonna pass.
Amen.
I'm gonna pass.
Okay,
No, that's right. I have to stop.
let's get the party started here. So, first little shot of snow. That's pretty cool, right? I love it. All right. Anyone else favorite season, winter? Yeah, see, there we go. I got some friends. It's nice. It's always good to have friends. So on Friday, we talked about this idea of combined loading, right? We went through this little example where we had a pipe, say it was affixed to a wall and it cantilevered out, and it had a couple applied torques to it, and then it had an axial compressive force applied to the end of it, okay? And when we do that, we went through and we figured out what is going on with respect to the stresses, right? Our normal stresses and our shear stresses at 2 points along the length of this pipe. We could then kind of devise these, what we call stress blocks, which are essentially just the stress state at a given orientation and location in our element, right? So in this case, we looked at what was going on, say on H, in these points H and K, right? Which were oriented, one face was oriented perpendicular to the axis of the pipe, and then the other face was oriented parallel to it, right? So we could figure out what's going on the face that's perpendicular, which in our case, there was a normal stress associated with the normal force that was in the pipe. And then there was a shear stress that was acting on these vertical faces, right? The face is perpendicular to the axis based on the torque. And we talked about equilibrium, which we will talk about again here shortly. That essentially results in this shear stress acting, right, equal and opposite on all four faces in order to keep this thing from twisting, right, spinning into space. So we'll hold it. So to maintain equilibrium, they look like this. So we got our two stress states. Well, when we have combined loading, right, we're getting outside of this simplified world of just having axial load, just having torsion, right? We're going to have torsion and axial. So now when we cut it perpendicular, we have kind of these combined forces like that are happening at the exact same time. Well, what that does is it makes it so that if we were to look at a stress state at a given angle, so if we took this block, we rotated it, or we decided to, say, cut this shaft at a 45, right? And then we oriented our block at a 45 and we were looking at what's going on these stresses, right, on these four faces. What happens is the combined loading, right, the torsional shear stresses and the axial stress from the normal force, they influence what's going to happen at an orientation. And so what can happen is that the stresses we may look at that are perpendicular and parallel to the applied forces might be less than what might happen at a given orientation. So you can get maximum stresses at a, say, 54 degrees, and that's all based on the applied loads, okay? And so in order to calculate what is the worst case, we need to look at worst possible demands at any orientation so we jump to chapter 12. Sorry. We jump to chapter 12. And chapter 12 shows us how do we transform, right? We're gonna have a known stress state. That's what we would call the stresses that we just calculated, right? That's the points H and K. We were able to calculate these fairly easily, right? We oriented the block with respect to the pipe so that it was perpendicular. So we have this normal stress. It's acting on the pipe. We have this shear stress acting on the pipe due to our torques. So we can figure out a known stress state. And so what Moore's circle does, it allows us to take this known stress state, plot this known stress state graphically, right? And it's a visual way of transforming and developing what are our maximum stresses that might be at some off angle of rotation, so that we can use those max stresses to design our member, right? Because ultimately we're finding our worst case demands, so we can relate that back to capacity, right? We're gonna have an allowable stress. The pipe can only handle so much shear stress or so much normal stress, right? It's gonna have an allowable yield stress. We can't exceed that. So Moore's circle allows us to do that. So before we dive into Moore's circle, everybody get that? We good there? We're gonna, what's that? Oh. It's all right. That's all right. That's why I ask. We're gonna dive into stress transformations, okay? But before we get to Moore's circle, we're gonna talk about, right, sign convention. And more importantly, we're going to simplify in this class. We're gonna go from this 3D stress state, right? Because in reality, we live in this 3D world. So there is not only a width and height to our block that we might be looking at, but there's a thickness to it as well. And sometimes if we deal with 3D stresses, so this is a 3D stress block. Oh, and this is chapter 12, sections 1 through 11. Okay. So if we look at a diagram of a 3D stress state, okay, so instead of having now a square, right, a plane, we have a cube, and on this cube it has a bunch of different stresses on it, okay? We have our normal stresses, right? Sigma x, sigma y, and sigma z. Those are all oriented in the axis, right? Normal to the axis in which we've devised, right? So x, y, and z. We have then our shear stresses, okay? The nomenclature for this is we have tau yx, right? Well, tau yx is the shear stress on the y face acting in the x direction, okay? Tau yz is the shear stress on the y face acting in the z direction. Right? Similarly for each of the other sides, right? So we have tau xy, tau xz, tau zy, and tau zx, right? So the first letter is the face in which it acts, right? Is it on the y faces or the x faces or the z faces? And then the next letter is which direction is it acting, right? Is it acting in parallel to the x-axis, the y-axis, or the z-axis? Okay. So if we look at this one first, right? Tau yz. So that is the shear stress on the y face in the x direction. Right? Oh, sorry, z direction. The fuck am I doing? Oh, I got this, this is wrong here. This is x. Wrote it down wrong, but read it right in my notes. Okay. So shear stress on the y face in the x direction. We have this 3D stress block, right? And these stresses are coming from loads, right? They could be torsion, shear, axial, bending. We're going to get to bending later. Okay. So based on our known loads, the configuration of the element that we're analyzing, okay, we could develop these stresses. Right? And as I mentioned, these normal stresses, sigma x, these are normal stress on the x-axis, right? Normal stress on the x-axis. Well, one beautiful thing about, one, this class, but two, in the real world when we're designing, especially machine parts, structural elements, okay, a lot of these stresses actually go to zero because we're dealing with things that are thin-walled, so like this wide flange, for instance, okay? If we were looking at a stress block on the very edge, that one surface was, say, the edge of this member, right? That stress is zero, right? It's atmospheric, it's out here, okay? So if that's the case, we then assume that sigma z, tau zx, and whoop, what the hell was that? Tau zy equals zero. We call this plane stress. Simplifies things quite a bit. So we essentially have nothing going on in this outside face of this block, right? No sigma z, tau zx, or tau zy. So nothing going on in the z faces, right? Plane stress. Well, we also need to know, right, if we start looking at plane stress, which we've already somewhat done some analysis in that previous example, right, where we drew our stress block, there were no stresses on the outside of that pipe, right? So we drew just a block and it had normal stress and shear stress. And we talked about this idea of these shear stresses and how we really figured out the stress on one edge of this block based on tau max is torque times the max radius divided by the polar moment of inertia, right? We went through that equation to figure out what our maximum shear stress was. We applied it on one side. And then based on equilibrium, we know that some of the forces in the y direction have to equal zero, so these two have to be equal to each other. We also know that because summing the moments, say about the origin point 0, this block can't be twisting off into space. And so that results in these equal and opposite forces on the top and bottom as well, right? Trying to twist it the other way. So in order to conduct this analysis, we need to have an understanding, or we want to know, relationship between tau xy and tau yx, right? Essentially what we're doing in this figure is we're taking this stress, multiplying it by an area. The area being the width or the height times its thickness, right? So tau, let me zoom in there so you can see this. So as I mentioned, we do an equilibrium analysis on a stress block. As I mentioned, we've already done. That's okay. So if we step back and do an equilibrium analysis, we want to know that the actual shear that's acting on these faces, right? Knowing that stress is force over an area, so stress times area is force. So we can't do equilibrium on stresses, so we need a force. In order to get a force, we multiply by an area. So if we know that tau xy, right, so that would be shear stress on the x face in the y direction. So both of these are tau xy. We know that our shear is tau xy times dy, which is the height, right, the length. The width or the thickness is dz. That's in and out of the page. So we would end up getting our shear force. So we assume small area, say dx times dz, or dy times dz, right? Those are our areas on both of those faces. This allows us to determine forces so we can sum moments about 0 or sum moments about the origin, set that equal to 0. And we get that our shear forces are equal, right? Essentially what I've explained. That based on summing forces and summing moments, we get that the shear force on all four sides, right, is equal in magnitude. It's opposite in direction across the block, right? And top and bottom. So that we can, summing forces in the y direction, we still get 0, right? These two forces are canceled out. Summing forces in the x direction also equals 0. And then if we sum the moment about any point, right? You can way out here, down here, these forces counteract each other. And they do so because they're all equal to one another. Right? So the directions are always going to be the same relative to each other, right? So if you had a shear force here that was pointed upward, then all of these other shear forces are going to be opposite, right? To maintain equilibrium. Yes, Brendan?
And then so the V denotes shear force. So see how
V, the big V. Yep, this is force. Because you can't do a summation of forces or moments without forces, right? And so we start out with a stress. We multiply it by an area to essentially establish a force, and then we sum the moments to the force. What's that? Is this what you want? Flying. You should see this page. A lot more to go. I'm trying to cram it all on one page. Okay. Well, now that we've established one, we're going to be dealing with plane stress, right? We're going to be looking at a stress block that has no stresses on the z faces, right? No normal stress, no shear stress, right? All of these stresses are 0. That simplifies things. And we've also established that once we can figure out one of these shear stresses, we know all the shear stresses that act on the block, right? They're all in relative direction based on this, okay? So now we need to establish, well, what is our sign convention for our stress block? What's positive shear stress? What's negative shear stress when we're looking at a block that looks something like this, right? We have directions that are associated with that. So if we look at our signs, okay, it's kind of so it's like the positive times the negative is a negative, right? A negative times a negative is a negative, and a positive times a positive is a positive. Got that? Okay. So if we look at this stress block on this coordinate system, right? And we use this coordinate system to say that in the positive direction, right? We have a positive face. And say we have a negative face. It's facing the negative side of the coordinate. Positive side, right? Negative side. And then we have directions to those shear stresses, right? So you have the face in which the shear stress acts, which would be either positive x, positive y, negative y. And then you have a direction in which that force acts, right? So you have this force that's acting in the positive y direction, negative y direction, positive x, negative x, right? So we use that product rule, essentially, right? A positive times a negative is a negative, and a positive times positive is positive, negative times negative is negative, right? Say that 10 times fast, damn. Okay? So a positive face that has positive stress is positive, right? So a positive face that has positive stress, right? It's acting in the positive direction, is a positive. So we've got, right, positive face. It's on the positive y face. It's acting in the positive x direction, this stress is positive. If we look at the x face, right? This stress is acting on the positive x face. It's acting in the positive y direction. It's also positive. Positive, positive, positive. We've got this tau yx that's in the bottom down here, okay? It's acting on the negative y face. It's acting in the negative x direction. What does that mean? There we go. And then same goes for the last one, right? It's on the negative x face. It's acting in the negative y direction. Two negatives make a positive. So we got negative, negative, positive. So you essentially have a stress block that's undergoing positive shear stress, right? It's positives on all sides. So now we get to write all that garbage out. So, positive face has positive stress. Positive plus a positive is a positive. Another case we could have a positive is if we have a negative face. And it has negative stress, negative, negative, we get ourselves a positive, right? Well, we can have a negative shear stress, right? In order to have negative shear stress, you might have a positive face that has a negative stress. So positive face, negative stress. We give ourselves a negative shear stress. Maybe we have a negative face that has positive stress on it. So negative face, positive stress, we have ourselves a negative, right? Questions there? So this block here is under positive shear stress, right? Okay. So we figured out we're dealing with plane stress. We figured out that our shear stresses are equal on all four sides. And we figured out what is our sign convention for our shear stresses, right? We know normal stresses, right? Outward is positive, tension. Towards the surface is negative, that's compression. We established that a long time in the axial chapter. Well, if we look at plane stress, in this figure, I'm sure all of you remember it vividly. I doubt it, but we went through this. This is in the notes, okay? This was back in, so if we go back to chapter 1. Right, that's axial chapter. We go back to that, we went through this example, right? And if we look at a member, so if we have an axial member like we do in the diagram, and it's loaded in tension as shown in the diagram. What is that? Tensino. Tension, loaded in tension, okay? Our max stress we determined during that time. Call this sigma max, right? Occurs on face AA. Right, that was this face right here. All right, if we drew a cut right there. And that is normal, that face is normal to our load P, so that our max stress equals our force P over area, right? Normal stress is normal force over the area in which it acts, right? And that area in which it acts is an area that is normal to force. In this case, when we looked at this axial member, we had a normal surface that was a cut, right, at A. So maybe we can just draw a little A, right? Say this was block A, similar to what we just did with the pipe and torsion and axial load. We've got this little stress block that's oriented as shown, perpendicular, right, to our normal force, right, or normal to our force. Well, if you remember here, we actually had a homework assignment where we looked at, I think it was a weld on a plate, right? We started looking at the stresses on that. So if we cut at an angle, that cut experiences a combination of normal and shear forces, right? Which essentially results in normal stress and shear stress, right? So we cut this axial member, right? Just has one force on it, P. But based on the orientation, right, we rotated this stress block. We were no longer looking at the stresses that were normal to our applied forces. We started looking at the stresses that were oriented at a given angle. Right, so we cut this member at an angle had this angle theta. We might call this new stress block we're looking at B, stress block B, right? Oriented along this cut plane. We want to figure out what kind of stresses are happening on this cut plane. So in order to do that, we oriented essentially a stress block that would go onto it. So if we looked at a stress block at A, we had a normal force, right, sigma x, that's running down the axis of our axial member. In our case, though, right, we had 0 normal force in the other direction, right? right? Stress looks something like this. It's just normal, outward normal from the face of that cut. No stress is perpendicular to that. But we realized that as we cut this, right, we needed to maintain equilibrium. So in order to maintain equilibrium, right, overall, the resultants of our normal forces on this surface, normal and shear forces on this surface, had to equal P, right? So we ended up getting normal and shear forces. So if we looked at our block B, for instance, and it was oriented at our angle theta, when we cut this member at an angle, right, we now have shear stresses and normal stresses. Well, because we have shear stresses and normal stresses, we end up getting a stress block that looks like something like this, right? We start seeing normal stresses, we start seeing shear stresses. And if you go through the derivation of what the stresses look like, right, the normal stresses, sigma n is P over 2a, 1 plus cosine of 2 theta. And the shear stresses are negative P over 2a times the sine of 2 theta. Well, when theta is 0, right, sine of 0 is 0, we have no shear stresses, right? So if we had a plane that's oriented vertically, as we start rotating that though, right, and rotating this block, we end up getting normal and shear stresses that occur. And if we were to plot out these normal and shear stresses for different thetas, we would get a relationship that looks something like this. Okay. So as you can imagine, at 90 degrees, our normal stress turns to 0, right? Because this block essentially rotated 90 degrees. So our face that originally started out with all the normal stress has 0 stress on it, right? Because our face, we essentially rotated this block 90 degrees. So we have no stress on this top face. So this face that we originally had stress on, we rotated the block 90 degrees, we no longer have stress on. But that means perpendicular, they didn't plot in this, which I wish they would have, is the stress on the y face. So this would be our x face. If we plotted the stress on the y face, I'm going to do it in green. That is pretty damn good. Wow. It would look something like this, right? So at 90 degrees, that face that used to be on the top is now on the side. So we have that full normal stress, and it works this way. So what does that mean? Well, if we orient it at a 45, we essentially have half the stress on each of our faces. So if B was oriented at 45 degrees, right? If you added up sigma x and sigma y, they would equal the original sigma x, right? This original normal stress, which makes sense from equilibrium standpoint, right? We've got this applied P force on our axial member, and that P force has to be carried through this block, and so we need to maintain equilibrium. So the normal stress is essentially taking both of these guys and adding them together. All right, so it looks something like this. So, knowing that there is a relationship, right, this almost sinusoidal relationship as we rotate, because overall we're still trying to maintain equilibrium, okay? More, I don't know what first name, last name, who this person was, okay? But they came up with this circle, which is a visual representation of essentially this graph. And so what do you get to do? Well, you get to plot a known stress state onto this graph, right? And visualize if you were to go from theta equals 0 to theta equals 180, what that stress state's going to do, okay? Wow, I thought I gave you guys more than that. It's okay, here we go. You guys are gonna love it. What's Moore's circle? Well, it's just that. It's a circle that's plotted on a, get out your straight edge. So on an axis, okay? It's just graphed. Do something like this, okay? I'm skewing it to one side, but it doesn't necessarily have to be, because I'm going to be plotting what we just went over for this axial member, okay? So we have two axes, as normal, right? An X and a Y. Well, on the x-axis, we plot our normal stress, okay? The x-axis, we plot our normal stress. That normal stress is plotted based on that normal stress being tension or compression. If that normal stress is tension, right, or positive, makes sense, we'd be on the positive side of the y-axis. So this would be sigma tension, right? Everything on the right side of our y-axis is in tension, right? If we're going to plot it, normal stress. So you can imagine anything on the left-hand side is in compression, okay? What the hell is our y-axis? Well, our y-axis is our shear stress, right? It's the only other thing we have to really plot on our stress block, right? We know our normal stresses and we know our shear stresses. So we're going to plot our shear stresses on this y-axis, okay? Don't ask me why Moore decided to do this. It's just the way that everything works out, I'm sure, on the transformation side of things. But positive shear is downward. Well, I'm sure you guys have already realized, but positive shear or what we call counterclockwise, right? It essentially tries to twist our block counterclockwise. Is on the bottom side. And then we have clockwise rotating shear. Well, that's on the negative side of our axes, right? So positive is downward, okay? Positive for shear is downward, which if your shear stress makes your block twist counterclockwise, it's positive on the downward side of our x-axis. If it's clockwise, all this negative shear. And we're on the upper part, right? The top part. We're above our x-axis, okay?
So it's like a moment going clockwise negative.
Yeah, so if we go back to our stress block, right? So if we were going to look at this stress block, and we were going to plot, right? The intent is to take a known stress state okay, and plot those values on the graph. And then those values create a circle. Those are the outermost, it's on the perimeter or circumference of our circle. We can create a circle from that. And then we know that if we were to rotate those points on that circle, we are effectively transforming the stresses at any given angle. So we can figure out, and I'll show you here, the point at which we get maximum shear stresses, or the point at which we get maximum normal stresses with no shear stresses, and things of that nature. So you would go through and you'd have a known stress state. Say this was the known stress state where we have tension on two faces, normal, and then we have shear stresses, right? So you'd go to this and say, okay, I'm going to plot my X normal stress, and that's attached to this shear stress, right, on the X face. This shear stress on the X face is rotating this block counterclockwise, right? So it would be on the bottom side of our Mohr circle, counterclockwise. So we would plot a positive tension, normal stress, associated with a shear stress that was down here. Then if we looked at the stress state that's happening on the Y face, right? We've got a normal Y stress. We've got a tau YX stress, right? Shear stress. Whoa. Okay? And so we could plot that. In this case, though, this pair of shear stresses on the Y face makes this block want to spin clockwise, right? So it would be at an equal distance above the axis as our first plot point was below, right? That's what aids us in getting even though both of these are positive shear stresses, right, you're going to plot one below based on the rules of Mohr's circle, and then one above, okay, based on the way it's going to try and spin that. So if we go back to this stress state at A. Whoa. Let's try this again. So we have this stress state at A. We started out by looking at our potential stresses at A. We have sigma x, right? We have tau xy and tau yx, right? Those are just the shear stresses on the x and y face in the x and y directions. And we have our sigma y. Well, we know based on our stress state up above, right? We're going back to this example where we have axial load. Stress state of 1, we only have normal force or normal stress, excuse me, on our x faces, right? So we can effectively get rid of tau xy and sigma y, right? There's no shear stresses on this element at A. There's no normal stress on the y face at A. We just have a normal stress that acts on the x face due to that axial load, right? That P force. So if we were to go through and try and plot this stress state on this Mohr circle, okay, we would start with on the x-axis, right? We have a sigma x, and we have no shear stress. Well, our sigma x is in tension, right? P is pulling outward. P is pulling outward, so we have this force that's in tension. So we're going to plot this point. It's going to end up being on the axis. That's not always the case. Should I do that? Should I not do that? I'm going to do that. So we're going to have sigma x, right, and tau xy. In this case, we have a sigma x. It's tension. It's on the right-hand side of the y-axis. Tau xy is 0, so we're on the x-axis. And we're going to get a point. Similarly, we're going to now look at the y-axis, right? If we look at the y-axis, we've got 0 stress, right? We have 0 normal stress. We have 0 shear stress. That makes it really easy. We're just going to plot this bitch right on the center here, right? 0, 0. That's easy. Again, though, if we were working with a different problem that had a different stress state, we're really plotting the points sigma y and tau yx, right? That's really what that dot stands for. But in our case, because we know the stress state, you know that those two values are 0. They end up right there. Based on those 2 points, okay, half the distance between them is what we would call the center. Right? We call this sigma average. Okay? This is what we would call our center. This allows us to plot the circle. Right? So even if these 2 points were, say, up here and say down here, we know tau xy and tau yx are the same, right? So even if we had shear stresses, we're going to be landing on points that are equal distance above and below the x-axis. Okay? So our center is always going to land on this x-axis. Once you establish the center, you need the radius. Right? In this case, it's really easy, right? It's just the distance between sigma x, the point that we graphed, and the center, right? Half the distance between the 2 of them. Okay? If we plotted 2 points that were equal distance above and below, right, you could still draw a line and you could figure out that average stress again, right? Which again is just the average of our normal stresses. Once you have center, you can figure out the radius. Radius is based on normal and shear stress, right? Essentially the hypotenuse, if you were to be putting a dot that was up here. So this allows us to draw this big ass circle here if I can. Where am I headed? Headed there. Back up there. Back up there. Pretty damn good. Look at that. Whoops. Back that. It's probably what all yours look like. Yep. Looks just like that. Holy shit. Okay, so you got this big circle, okay? So now we have essentially graphed all of the possible stress states for this element at any orientation, okay? Any orientation, pretty sweet. We call our maximum normal stresses with no shear stresses our principal stresses. That's essentially, in our case, what we graphed, okay? Not always the case, right? If like in our torsional problem, we had shear stress and normal stress, right? So we would have points up here and down here. We would have to rotate that stress block a certain amount to get to those points, right? But we would call this what we call sigma 1 and sigma 2. So sigma 1 and sigma 2 are what we call principal stresses. And they are the min and max normal stress and they occur where shear stress is 0. Which just happens to be our location A at this point, right? We essentially have 0 shear stress, just normal stress. We happen to have 0 normal stress in the one direction, but that's fine. Still principal stress, right? It's the point at which we have our minimum and maximum normal stresses. These are incredibly helpful when determining whether or not your element meets, say, allowable stresses, right? Allowable normal stresses. We're going to have, say, a yield stress, or what we would call a stress in which we're constituting this element to fail. And then we say we're going to put a factor of safety on it, right? We're going to reduce that failure stress to an allowable stress. And we would relate that allowable stress back to these principal stresses, right? Because it's the maximum and minimum stress that are going to occur on our block, which is where we have 0 shear stress. We are also going to be able to determine from this our maximum shear stresses, right? we know at the top and bottom of this circle it's always going to be the case that tau max, when we plot the point on the top, that's going to equal the point on the bottom, right? They're always equal. And you'll know the direction of them on that given face based on clockwise or counterclockwise, right? So in our case, for our example, we were looking for our worst case shear, given our initial stress state, right? Is this normal stress state, or A? We've got this rotation on Moore's circle of 90 degrees. Well, something to note, super important, okay? Rotation on Moore's circle is twice the rotation in the real world. Okay? Twice the rotation in the real world. How does that make sense? Well, if you look at this Moore's circle, right, and we go back to this graph where we plotted the change in stress as we change degrees, at 180, we're essentially right back to where we started, right? Well, if you look at Moore's circle, if we started at this point and we go 360 degrees, we're right back to where we started, right? So we got to go twice as far in order to get the same amount. Make sense? Lambda is twice theta. All right. Till next time.